College Trigonometry, Chapter 10, Section 7. We'll do a brief overview of Chapter 7, Section 4. Parametric equations were covered in our book for the first time in Chapter 7, which we did not go over. It kind of falls in between the algebra, college algebra, and the trig courses, so we actually didn't see this the first time around. So we're going to take a couple of minutes and go over exactly what we mean when we talk about parametric equations, and we're going to talk about how to convert them to standard equations without using trig functions, and then we'll go to Chapter 10, which is doing the same thing, only with trig functions involved. So parametric equations, a plane curve is a set of points, x, y, such that x equals f of t, y equals g of t, and f and g are both continuous on an open interval I. The equations x equals f of t and y equals g of t are parametric equations with parameter t. To put this a little more simply, parametric equations define both x and y in terms of a third variable that is called t. And they actually allow you to graph curves a little more easily and a little more fluidly. They always come in pairs because you have to have one that defines x and you have to have one that defines y. If you're going to graph them on your calculator, and you can, you need to be sure that you switch to parametric mode. So if you go to mode and then go down to where it says function, parametric polar, choose parametric. And then when you hit y equals, you will notice that you have two pairs that you need to enter. You have x1t, y1t, x2t, y2t. So you need to, it gives you a place to put both the x and the y. And so you just need to make sure you do that when you go to graph the parametric. Plane curve defined by the parametric equations, x equals t squared and y equals 2t plus 3 for t on the interval -3, 3. Graph the curve and find the equivalent rectangular equation. Okay, so let me walk you through how to do this, although if you want to try it on your own, feel free to pause the recording and give yourself a challenge. But what we're going to do is, if you want to do it by hand, you make a table corresponding to values of t, x, and y. So in other words, you're going to pick values of t and then figure out what that gives you as far as x and y goes. So for example, they used -3 for t, and you get 9 for x, you get -3 for y, and first point. Here's some further examples of points that they found. They went from -3 to 3 using integers for t because it said to go from -3 to 3. And we've got our corresponding x and y values. And then you just graph this on an xy axis, and t kind of fades into invisibility there. And you see that we have a parabola that is facing sideways. In order to change it, what you have to do is eliminate the t. So what you'll do is you will solve one of the equations for t, and in this case they chose to solve the y because it was a little easier than having to deal with the square root. And they got t equals y minus 3 over 2. And then in the equation x equals t squared, replace t with y minus 3 over 2. And then they simplified that, so you see we have 1/4 y minus 3 squared, and that is our rectangular equation that matches the two parametric equations. This is a horizontal parabola that opens to the right. If you remember when we did conic sections in Algebra 2 or 3, depending on which of those classes you were in, this is the form of an equation for a sideways facing parabola. And here we have your graphing calculator. Again, put it in parametric mode. For x1, make it t squared. And notice when you hit the x button, it's going to come up as a t because you're in parametric mode. And y1 is going to be 2t plus 3. And then you see the window there. The window they get, or the table rather, they give you the values for t, x, and y. And there we have the equation. When you go to the window, you can set your max and mins for x, y, and t. Now try graphing this equation. Try this one on your own. Pause the recording, give it a try, and resume to check your answer. Now, if you want to, what they did first was they went ahead and changed it to rectangular form. And it's kind of a mess when you do that. You get the square root of 4 minus x minus 5 over 2 squared. and it's going to be an ellipse. They kind of simplified a little bit and changed it to a rectangular form. You don't need to completely do that. And remember, we're really just going over what parametric equations are so that we have an understanding of them when we put some trig functions into these. So don't worry too much about the conic section relationship here. Now, we're going to examine parametric equations using trig functions. And here are some examples of trig functions that were used in parametric equations, some graphs where they used parametric equations with trig functions in them. We have a little, well, it's not exactly a smiley face. I don't know what that is. Astonished face. Maybe it's a face of somebody studying way too much math. Then we have kind of a design, and then we have our favorite, maybe not, I don't know, is pi or e your favorite irrational number? Anyway, one of our favorite irrational numbers, e. So, using what we talked about, we're going to graph x equals 2 cosine t and y equals 2 sine t. Now, you need to make sure you're in parametric mode, and notice it's from 0 to 2 pi, so you're going to want to make sure you're in radian mode, and 0 to 2 pi, and find an equivalent equation using rectangular coordinates. Pause the recording, give it a try, and resume to check your answer. All right, so graphing it, you get a circle. Now, you may have looked at your graph and said it looked more like a football than a circle. That's because we've talked about this before. It's kind of like your graph has a rectangular window, so when you graph it and you have the same max and min for x and y, the x values, the x hash marks are going to be more spread out. It's kind of like when you have a TV, you have an HD TV, but you have a standard program that was originally recorded and it's square, and you hit the HD zoom and it spreads it out over the whole thing, but it widens it and it distorts it. That's kind of what's happening with your graph. So what you can do is after you've graphed it and made sure you have the entire circle in the graph, go zoom and choose zoom square from your menu, and that will automatically make the values so that they're spaced evenly, and it will give you a nice circle like you see here. To verify this is a circle, consider the following. X squared plus y squared equals 2 cosine t squared plus 2 sine t squared, so they just added the x values together, which remember, x squared plus y squared equals r squared is the equation of a circle. And then what they did was they squared that, and they got 4 cosine squared plus 4 sine squared. Factor out the 4, and we have 4 times cosine squared plus sine squared, which is 1, which gives us 4. So our equation is the same as x squared plus y squared equals 4, and it's just a little easier to graph. So it's a circle with center 0, 0, and radius 2. Okay, now let's try this one. We're going to graph the plane curve defined by x equals 2 sine t and y equals 3 cosine t. Pause the recording, give it a try, and resume to check your answer. Now this one is going to give us an ellipse, and the reason it gives us an ellipse is notice that the number in front of the sine and cosine are different. And when that happens, one side is going to be more elongated than the other. You see there where they have solved it so that you have the rectangular coordinates. You didn't have to do that, it didn't tell you to, but you can see the graph of the ellipse there. The path traced by a fixed point on the circumference of a circle rolling along a line is called a cycloid. Think about it this way. Think about taking a tire, maybe your bicycle, and you make a mark on the edge of the tire, and then you roll the tire down the sidewalk. The path traced by that dot as the bicycle goes, as the wheel goes around, is called a cycloid. And it's defined by the equation x equals at minus a sine t and y equals a minus a cosine t for t from negative infinity to infinity. So let's try graphing this. We're going to graph the cycloid where a is 1 and t is from 0 to 2 pi. So you're going to take the equation we just had, and it's going to be 1 for x, it's going to be 1t minus 1 sine t. For y, it's going to be 1 minus 1 cosine t. And graph it. Give it a try, pause the recording, and resume to check your answer. Okay, so there's really no simple way to find a rectangular equation for this, so we did plot some points and made some ordered pairs, And there you see the progress. And what they're showing you there is the wheel itself. And you can kind of picture in your head as that wheel rolls along the axis, that dot is going to follow that blue curve. This is what it would look like on your graphing calculator. It's just a little bit of, for your information type of deal here. Interesting physical property of a cycloid. It says if you have a flexible wire that goes through points P and Q, so let's say you've got two tacks on a board, one's at P and one's at Q, and you attach a flexible wire through it, and before you attach it, you put a bead on it, and you hold the B at P, and then you let it slide due to gravity. Let's say it's frictionless. The path that requires the shortest time to go down takes the shape of an inverted cycloid. So parametric equations are frequently used in computer graphics to design figures and letters, especially when curves are involved. So here's a challenge. See if you can come up with a way to graph a smiley face using parametric equations. Remember, you're going to be using sine and cosine. The number in front is going to determine the radius of the circle. So you're going to want to be doing some circles for this and see if you can add and subtract things to move the center of that circle around a little bit. If you want to do the challenge, go ahead and pause the recording, give it a try, and if not, resume and see how you do it. So for the head, you're going to use a circle centered at the origin, and the radius, we're going to let the radius be 2. It can be as big as you want, but for this one we did 2. So x is 2 cosine t and y is 2 sine t. And t is going from 0 to 2 pi. So there's small circles for the eyes. What we're going to do in the first quadrant, we're moving it over 1 and up. So it's going to be 1 plus 0.3 cosine t. The 0.3 is going to determine the radius. So we want it to be kind of small. And then y, 1 plus 0.3 sine t. So that's going to give us the one in the first quadrant, and that's going to be a circle centered at 1, 1. That's where the ones are coming from, with a radius of 0.3. In quadrant 2, you can do the same thing, except notice what they did is they did negative 1 plus 0.3 cosine t, so that just moved it to the opposite side, and then they raised it for the y value the same amount, 1 plus 0.3 sine t. So that gives us the same size, and it gives us the same height on opposite sides of the y-axis. For the mouth, they're going to use the lower half of a circle, so they did x equals 0.5 cosine 1/2 t, and y equals negative 0.5 minus 0.5 sine 1/2 t, which is a semicircle centered at 0, negative 0.5 with a radius of 0.5. So that's going to make sure that that 1/2 t gives you only half the circle. The rest of this is some additional practice, so pause the recording as you go through these, give them a try, resume the recording to see how you did.